show that there are integers x and y. Such that R is equal to xm plus yn. mx plus ny, but same thing. Since n and m and n are I think you can pretty much guess what I am trying to write here, are relatively prime. 1 is equal to Sm plus Tn for some integers s and t. This implies you just multiply both on both sides by r. That will give us r is equal to rsm plus rtn. So the integers x and y they were talking about are respectively rs and rt. That's it. I need some ink. Looking at this exercise, you can notice one thing. If you already know something about vector spaces, I may make a remark. If this goes over your head, don't worry, we will eventually get to vector spaces at some point. See, we are saying that these are linear combinations of m and n. Okay, in the language of vector spaces, that has a meaning. Now, unlike how we do calculations in a vector space where the scalars are coming from a field, here the scalars are integers. So if we are considering only integer combinations, then m and n together are behaving like a basis for the space of all integers. Integers don't form a vector space in that sense. I am just simply making an analogy. If they are relatively prime, then they sort of behave like a basis for the vector space. It's just an analogy. There is no mathematical basis for what I am talking about. Okay. Okay, then a problem from number theory. All these are from number theory, but this is specifically number theoretic in nature. Exercise 14. Okay, with that much ink it will be even more dirty. Let P, Q and R be primes other than 3. P, Q and R be primes other than 3. So each one of them is a prime, but it's not equal to 3. Show that three divides p square plus q square plus r square. It will always be divisible by 3. Okay, so this one, oh, I haven't written any hint also. How did I approach this problem? These are primes and these are, none of them is equal to 3. Okay, yeah, I remember. Okay, so note that by the division algorithm, if I divide p by 3, then there are 3 possible remainders, 0, 1 and 2. But I cannot have the remainder 0, because since p is a prime, if it is divisible by 3, it has to be equal to 3, and that is not allowed because it's given that all of these primes are different from 3. So the remainders when I divide p by 3 are only either 1 is only either 1 or 2, and similarly for q and r. So we can write like this: since okay, before we write any argument, we can simplify the notation. Let p prime be p mod 3, q prime be q mod 3, and r prime be r mod 3. These are the remainders of the numbers p, q and r respectively when they are divided by 3. Since p, q and r are all different from 3, we have p prime, q prime and r prime belonging to this set. Each one of them is either 1 or 2. Okay, now according to their values, several cases will appear. We can reduce the number of cases effectively by considering cases like, say for example, p prime and q prime are equal to 1, but r prime is equal to 2. That is one case. Q prime and r prime are equal to 1, but p prime is equal to 2. That is actually another case. But these two cases are really the same thing, because there is no real distinction between p prime, q prime and r prime. They are just some remainders when we have divided p, q and r by 3 respectively. So we can cut down on the number of cases. If two cases will be absolute, namely one of them is the one where all of them are equal to 1, and the other one is the one where all of them are equal to 2. If p prime is equal to q prime is equal to r prime is equal to 1, then clearly p square plus q square plus r square, we want to show that this is divisible by 3. So that means this modulo 3 should be equal to 0. The remainder that we get when we divide this 1 by 3 should be shown to be equal to 0. So this mod 3 is equal to, now you apply the result of that exercise where we proved that a plus b mod n is equal to a prime plus b prime mod n. So instead of actually making this calculation and then dividing the result by 3 to find the remainder, we can divide p square, q square and r square by 3, find the remainders and then add them up and then divide that sum by 3 to find the remainder. That is for sum, but we also have another one for product. So this is actually equal to p prime square plus q prime square plus r prime square modulo 3. If you didn't get what I am talking about, then go back to which one is the first one, the first exercise. Oh, I cannot say of today because this may be 2 videos, no? Exercise 9, you go back to exercise 9, we are applying the result of that here. So this is equal to, now this is 1, this is 1, this is also 1, so 3 mod 3, which is equal to 0. So that means in this case, this expression is actually divisible by 3. On the other hand, if all of them are equal to 2, then this is equal to p prime square plus r prime square. So 2 square is 4, 3 times 4 is 12. 12 mod 3 is again 0. So in that case also this is divisible by 3. The problem is that if I apply pressure and then try to rub it off, it's getting smeared. I think it's because of the humidity. This part of the world is extremely humid. And recently the humidity has gone up because of incessant rainfall. Okay, now next we come to the cases where say exactly one of these 3 is 1 and the other one are 2. Next, assume that exactly one of p prime, q prime and r prime is 1. Exactly one of them is 1 means the other 2 must be equal to 2. We assume without loss of generality that p prime is equal to 1, then q prime and r prime must be equal to 2. In this case, p square plus q square plus r square mod 3 is equal to p prime square plus q prime square plus r prime square mod 3. Okay, so here we will have 2 square plus 2 square, 4 plus 4 8 plus 1 square 9. So 9 mod 3, that is again 0. Finally, there is effectively only one more case left. Assume that exactly one of these is 2. without loss of generality that, say the first one is 2, p prime is 2, then the other two are forced to be 1, in this case we have mod 3 is equal to p prime square plus q prime square plus r prime square mod 3. Okay, now we have only 1 2, so 2 square gives us 4 and 2 ones, 4 plus 1 plus 1 6, so 6 mod 3, that is again equal to 0. So in any case 3 divides p square plus q square plus r square. Although we have seen the full argument, but just for the sake of fun you can take some actual values of p, q and r and see that the sum of their squares is actually divisible by 3. For example, if we take let us say we can take the smallest possible values of p, q and r. One of them can be chosen to be 2, the other is 5 and this one is say 7. Okay, then 2 square is 4, this is 25, this is 49. 78. Yes, 3 times 26, and nothing prevents us from taking these primes to be the same actually, or in fact 2 of them to be the same. So if one wants, one can take 2 square plus 2 square plus 5 square also. That will give us, this 2 will give us 8 plus 25. So here it is clearly divisible by 3. So in any case this will always be divisible by 3. Then exercise 15. Prove that every prime greater than 3 can be written in the form six n plus 5 plus 1 or 6n plus 5, where n is some integer, every prime. And this is a clear application of the division algorithm and primality of 3, of course. By the division algorithm, any integer is of one of the following forms: 6n plus 1, 6n plus 2, 6n plus 3, 6n plus 4, or 6n plus 5. That is because if we divide any integer by 6, the remainder is either 0 or 1 or 2 or 3 or 4 or 5. Accordingly, these are the possible forms in which the integer can be written. Okay. Now it is given that the integer is if the integer now is a prime which is greater than 3, then what can we say? Now let P be a prime greater than 3. We have to show that P can be written only either in this form or in this form, but in none of the remaining forms. We have to rule them out somehow. Note that not 6. 2 divides 6n, right? 2 also divides 6n plus 2. 3 divides 6n plus 3, and again 2 divides 6n plus 4. Since P is prime, P cannot be of the form 6n, because every integer of the form 6n is divisible by both 2 and 3, and clearly no single prime can be divisible by two distinct primes. Also, P cannot be of the form 6n plus 2 or 6n plus 3, since P is greater than 3. Note that P being of the form 6n plus 3 means P is equal to 6n plus 3 for some n. Now the only prime number of the form 6n plus 3 is 3, because if it is not 3, then you can see that if you are dividing this by 3, it's always divisible by 3. Okay, so we can argue like that. Since this integer is always divisible by 3, so if P is of this form, then this is also divisible by 3, but P is a prime, then P is forced to be equal to 3, which is also not possible because it's given that P is greater than 3. In this case, P is divisible by 2. So if this is our prime number, then it must be equal to 2, but then again this is contradicted. So that's why it cannot be of either of these two forms. So this has been ruled out, this one. This one also has been ruled out. This one also has been ruled out. And what about this one? Finally, P cannot be of the form 6n plus 4 because 2 divides 6n plus 4, same thing. Actually, I think you can compress these arguments into maybe 1 or 2 lines. You can make it more compact. I'm just going with the flow and seeing what's happening. So this is also ruled out. So this is also ruled out. That means we are left with 6n plus 1 and 6n plus 5. Hence, P is of the form 6n plus 1 or 6n plus 5.